Welcome to podcast number 99. And today we're talking about the second part of this podcast series. In 98, we talked about marsupial UAVs or you know, unmanned aerial systems. And this is where you have a parent UAV and then you have other little UAVs that is carrying along and it can deploy. And in that podcast, we were talking about what these were and some other basics. Now we're going to be talking about the interference pattern between different UAVs. So if you have the parent UAV, then you have a child UAV just above it. And obviously the wash from the different propellers are going to affect the aerodynamics as well as the objects themselves. For example, the body of the parent UAV. So we're going to go through this paper, the second half. It's called Ground Test and Numerical Simulation of Aerodynamic Interference of the Marsupial UAS. And this is, again, open access, so you can find it in the link in the description. So let's continue where we left off in the last podcast. In the last podcast, we're just looking at the effects of the parent UAV underneath the child UAV with and without the propellers moving. And it was such that the child UAV was like directly above the body. Now let's start with the effects of the child UAV above the propellers, so the rotors. Then there's a third area that we're going to look at as well, which is the intermediate regions. So when it's coming into these regions and leaving these regions. Let's first look at the child UAV above the propellers. So they say when the child UAV is located right above the parent UAV rotors, it is mainly affected by the rotors. The pressure below the child UAV is lower than that above, reducing the lift of the child UAV. And they have in figure 12 here the lift of the child UAV in the interference area above a rotor. So again, they have this graph with the parent rotors moving and them not moving. Oh, sorry, they have them with them moving in the experiment and simulations this time. And they have a hovering state. So in the hovering state, the child UAV typically produces about 4.2 newtons. And this is just enough for it to get off the ground and hover around because the child UAV is like 0.42 kilograms. So that's just enough. Then they have a red line which shows the effects of the like the lift with getting closer to the rotor from above. So you're coming down above the child UAV, coming down, getting closer to the parent UAV from the top. And they say as the child UAV gets closer to the parent UAV's rotor, the lift drops dramatically by about 30%. It drops linearly as well, with most of the decrease happening within the last 25 centimeters from the rotor. So once you get past 25 centimeters above the rotor, the lift starts to stabilize a little bit. So instead of being 4.2 newtons, it's now going to be about 3.8, and then just keeps climbing back up there, almost to 4.2. Interestingly, even above the rotor by 1 meter, which is the little UAV is only like 3 centimeters thick. So 1 meter is a huge distance away. You still get a deficit of the lift by about 5%. So that's quite a decent amount, even though you are so far away from the rotor still. So anyway, and this decrease is true regardless with the simulations and experiments. So their simulation results, which we went through last podcast, how to simulate rotors, their simulation at least with using a momentum source, that was good here. So we can see that just if you have the child UAV above the parent UAV's rotors to any extent, you're going to have a reduction in lift. It just is a matter of how much. And when you get very close, like within a foot, it's very dramatic. And in this particular case, they went down to about, I think, 10 centimeters above or 5 centimeters above the rotor, and it was still decreasing sharply. So once you get maybe 2 centimeters above, you might get like almost no lift, and it might even just fall straight into the rotor and get damaged. So they have the lift to power ratio as well, which we talked about again in the last podcast. If you haven't listened to that, go listen to that, and you'll understand a bit more about what this is. This is just a measure of efficiency, effectively. And they have the UAV rotors, the parent UAV rotors on and off, and the effects of this parent UAV on the lift to power ratio of the child UAV. So without the rotors on, there's almost no effect. So with the child UAV above, and you kind of expect that considering that there's nothing trying to pull the air out of the child UAV's rotors, so there's not really much of an effect there. However, when the parent UAV's rotors are on, there's a very large effect. So the drop occurs again in a very similar fashion where the closer you get to the rotors, the more non-linear it becomes, to the point where like 10 centimeters above the parent UAV rotors, the child UAV is only producing about 80% of the lift to power ratio that it usually would. So there's a massive reduction there. Also, even if you go to about 36 centimeters above the UAV, the child UAV is still producing a slightly lower lift to power ratio than what it should be without any interference, by about 5%. So again, that's to be expected considering we know what the lift curve slope was to begin with. So this is not that surprising. Now in figure 14, again, they have these really cool schematics which show the parent UAV diagram, like where this is, and then you have the child UAV above the rotor, and then you have colored in a shading of blue the distance from the rotor that the child UAV will be, and the effects on the lift. So the closer you get, the darker this blue becomes, and that indicates a greater loss in lift. So this is a very effective way of presenting information. I'm very impressed with this approach here. So in addition to this configuration, we also have now when the child UAV is starting to enter different zones around the parent UAV. So it's not just hovering above the rotor or just above the body. And this is far more complicated. There are two transition zones that we're going to be looking at. The first is when the child UAV is already inside the envelope of the parent UAV, so it's above it to some extent, whether it's above the body or above the rotor and it's moving around. That's the first transitional area. The second transitional area is when it's away from the UAV and it's coming into the path of the UAV, the parent UAV, so above it. So let's say you're a meter away from the parent UAV, and then you start coming just above the rotor. That's the second transition area. To begin with, we're going to be looking at the first transitional area. So when the child UAV is above the UAV to some extent already, and it moves around. So this transitional area includes the body outside transition area and the rotor outside transitional area, these two different sections. And this section of this paper mainly studies the impact when a child UAV's horizontal direction changes. So it moves around horizontally, but not up or down. So in figure 15, they show the distance from the middle of the body that the child UAV is as it moves away towards the rotors. And this is described in centimeters, so 0 centimeters to 10 centimeters. And they have two different situations. One where the child UAV is 4 centimeters above the parent UAV. The other one is when it's 13 centimeters above. So when the projection of the child UAV on the body parent UAV gradually decreases, the lift coefficient obviously decreases as well, as shown in figure 15. In this interference area, the flow field is asymmetric. So that means that, as I mentioned earlier in the other podcast, when you have the child UAV not directly above the body, the wash from these propellers are going to affect the parent UAV differently. So the propeller that is closest to is going to get the most effect of it, and then the rotor further away is going to get the least effect, which makes sense. So both the suction of the nearby parent UAV rotor and the parent UAV body cause a lateral movement towards a nearby rotor. So in other words, as soon as this child UAV starts moving away from the body, there's a suction that pulls it even further away, even quicker. And this means that the child UAV starts moving out quicker. And in terms of the lift production, when the child UAV is 13 centimeters above the parent UAV, the lift production is fairly constant with the changing of height. However, when it's 4 centimeters above, there's a major difference, and we'll cover this now, why it is. So when it's located right above the body, the lift is 4.8 newtons. So that's quite high. That's higher than what it needs for hovering. And this is mainly because of the ground effect. It's effectively like it's not exactly ground effect because the parent UAV is not a complete ground. It's not extending out to infinity, but that's kind of the concept. So you get an increase in the lift production there. However, once you start moving away from the center of the body, more and more of the downwash of the child rotor is skipping over the parent UAV body. So there's less and less ground effect. So that's why the lift reduces, but also as you get closer to the rotor, then you have obviously some of that downwash being sucked in and you lose some of that lift there as well. So that's why when you get further and further away, so you're even not over the body anymore, you still get a reduction in lift the further you get it out. Then in figure 16, they show the lateral movement of the child UAV body inside this area. So in other words, as it moves away from the body, how much side force there is. And we can see that when the child UAV is very close to the parent UAV, this side force dramatically changes. Whereas when it's quite far away, so 30 centimeters above, this side force stays fairly constant regardless of how much you move to the side. So there's not this the derivative of the moment is not is zero effectively, whereas when it's very close to the parent UAV, the derivative is very negative. So that means it changes. So in figure 17, they show the lift of the child UAV in the rotor outside transitional area. So this is now the second transitional area where your child UAV is outside of the parent UAV and they start to come into the rotor area or just above. So when the child UAV moves from the center of the parent rotor to the outside, the effect of the downwash flow on the lift decreases approximately linearly. The lift gradient increases as the relative height decreases, as shown in figure 17. So in other words, the closer you are to the UAV, the parent UAV, in terms of height above, the more severe these effects become, which makes sense. Then in figure 18, they show the lateral moment again of this child UAV as it comes into the path of the parent UAV. And interestingly, it's not monotonic, so it goes up and then goes down. And let's describe this a bit more. Due to the suction effect by the nearby parent UAV rotor, the child UAV is subjected to a significant lateral moment, as shown in figure 18. And this lateral moment will increase first and then decrease with distance. The asymmetric lateral moment reaches the maximum when the child UAV is located at the tip of the rotor of the parent UAV, which may pose a threat to flight safety. Let's talk about this a bit more. So what they're saying is when the child UAV is far away from the parent UAV and it comes closer, the lateral force becomes greater and greater. And then once it reaches the tip of the rotor, so it's above and it's at the tip area, it then reaches maximum. And then when it goes further into the rotor area, it reduces. And the reason why this poses a flight safety threat is because when you have changes in side forces and any force really, it's dynamic. It means that it's harder to control. So it's harder to stabilize. So that's just what they mean there. And again, in figure 19, they have a really cool schematic showing the effects of this motion on lift as you move around the UAV. So pretty much anywhere you are outside of the body of the parent UAV, you get a reduction in lift. If you're above the body of the parent UAV, then you get an increase. That's the only area. So that's quite easy to keep in mind. So let's talk about now the mechanism of the aerodynamic interference. They have a lot of cool pictures here from CFD showing the streamlines and how the flow is moving. Let me zoom out slightly so you can see. And if you're listening to this on Spotify, you can probably see the video as well. If you can't see the video, then check out our YouTube channel and you'll see it there. So on figure 20, they show that when the distance between the child UAV and the body is relatively close, the airflow accelerated by the child UAV rotors is blocked by the body, which causes a redirection of the flow and it becomes parallel to the body. So this is why the ground effect occurs and the boost in lift. The airflow below the child UAV is squeezed, which leads to a significant pressure increase as shown in figure 20. So you can see just above the parent UAV, the pressure now is much higher than what it should be simply because of that ground effect. And that's where you get that extra buoyancy. Affected by this, the positive pressure of the child UAV body and your rotors increase. So what about now when the pressure distribution of the child UAV at different heights? So in figure 21, the pressure change on the lower surface of the child UAV body is shown in figure 21A. And this is important because it shows effectively the pressure side of the UAV. This is where, if you were to integrate the pressure underneath and the pressure on top, you get the lift then. Also, you need to take into account the rotors, but that's another story as well. So the lift of the child UAV becomes larger than the hovering state when you're over the body. Meanwhile, due to the limited size of the body, part of the airflow continues to flow downwards along the outside of the body, which reduces the pressure above the parent UAV. At the same time, a lower pressure area is formed at the nose and tail of the body. These result in slight decreases in lift. So in other words, because of this, you have lower pressure around these areas, the integration of the pressure around the entire UAV is lower. The downwash effect of the parent rotors causes a reduction in lift of both the rotors and the body of the child UAV. So again, when the propellers are working, you're sucking away flow from the child UAV, and that's reducing the lift, unfortunately. On the one hand, according to the blade element theory, the blade element theory is a theoretical way of calculating the not only lift but also the thrust of an object of a propeller. So according to the blade element theory, it's easier to do than regular CFD because you don't have as many properties to calculate, so it's quicker, but not as accurate often. But it depends on the situation. So according to this theory, the downwash flow increases the induced velocity into the child UAV rotors. The relative angle of attack on the rotors decreases then, resulting in a slight lift decrease in the child UAV rotor. So that's really cool. So because you're sucking flow more out of the rotors, the effective angle of attack of this flow to the rotors is now changing, which results in a reduction in lift. So on the other hand, the downwash acts on the upper surface of the child UAV, which increases the upper pressure on the upper surface, thus forming a negative lift, so a downforce. When the child UAV is closer to the parent body, due to the shading of the parent body, the pressure around the child UAV is large, blocking the influence of the downwash. As a result, the pressure on the upper surface is slightly higher than the pressure in the hovering state. As the relative height of the child UAV and the parent UAV increases, the impact of the parent body drops dramatically, which you would expect. And the downwash effect of the parent rotors is enhanced, resulting in a gradual increase in the pressure on the upper surface of the child UAV. When the relative height continues to increase, the influence of the rotors on the parent UAV gradually decreases until it is close to non-interference state at all. So we saw that in the other graphs as well. In other words, the further away you get from the parent UAV, the less effect you're going to be getting, which is good. So in figure 22, we see the flow field when the child UAV is right above the parent UAV rotors. So this is where you have the child UAV now, and it's like throwing air into the parent UAV, one of the parent UAV rotors. When the child UAV is above the rotor of the parent UAV, the airflow accelerated by the child UAV rotor passes through the parent UAV, the rotor of parent UAV, sorry, which changes the pressure distribution of the parent UAV rotor and reduces the lift of this rotor, as can be seen in figure 22. So that's not good. Obviously, the reduction in lift on this rotor will result in an imbalance of the force of the UAV, which could destabilize it. The alternatives are either you reduce the lift of one of the other rotors, or which means that you're not going to get as much lift, so you may not be able to hover, or you have to increase the RPM of this rotor, or if you can, change the pitching angle of the rotor that's being affected to increase the lift to stabilize this effect. So it's quite a complex situation. So in addition to these effects, they also go through the analysis of the safety flight boundary of the child UAV. So they go through where above this parent UAV, this child UAV can go while still maintaining safety, and where it can't go in terms of it will lose stability. And it's really cool how this novel approach that they're taking. So I want to go through this. So when the child UAV is in a position with a large lift loss or a fast changing lift, the stable flight control of the child UAV in the launch and recovery process may be challenged, so it may be compromised. In other words, when the lift is changing dramatically, your stability is compromised and you may fall out of the sky. In this paper, they defined a dimensionless parameter gamma to describe the rate of change in the lift position. And this is based on the change in lift with changing distance, so the derivative of that, and then the rotor radius of the child UAV and the weight of the child UAV. So the lift loss if the lift loss is less than 10% and the gamma is less than 0.3, these are used as indicators to plan a safe flight boundary for the child UAV. So in other words, we don't want the lift loss to be more than 10%, and we don't want the change in the lift, so the gamma ratio, the gamma parameter, to be more than 0.3. If either of these happen, then that's unsafe. So they just plot out some different areas where this child UAV can go without this happening, either having a 10% increase in a 10% drop in lift or a gamma of 0.3 or more. So in the interference area above the body, when the distance above is 6 centimeters, or is less than 6 centimeters, sorry, the disturbed lift of the child UAV is greater than 10 centimeters of the hovering flight. So that's a no-go zone then. However, when the height is less than 21 centimeters, the lift of the child UAV changes rapidly, which has a significant effect on the flight safety. The lift of the interference area around the rotor is interpolated by ignoring the influence of the body of the UAV, and a safe flight boundary near the rotor is obtained. So in other words, even though you're might only be 6 centimeters above the rotor, even though the lift is not reduced by 10%, you still have the lift changing dramatically. So you have to go above 21 centimeters to have a safe flight path still. and above the body of the parent UAV, this is 20 centimeters above the rotor, it's more like a dome. So when you go further away from the rotor center, the height that you can be above the parent UAV while still maintaining safety is lower. So that's good. So in conclusion, the results show that the influence of the lower parent UAV on the upper child UAV cannot be ignored. In the longitudinal direction, there is a strong aerodynamic disturbance above the parent rotors, with a maximum lift loss of 33% for the child UAV. In the area above the body of the parent UAV, the lift of the child UAV changes rapidly from a 27.4% increment to a 10% lift loss, which is why you got such a big gamma, that non-dimensional parameter that they use to specify the safety area of the UAV. In the horizontal direction, the lift of the child UAV decreases significantly, and there is an asymmetric moment pointing to the nearest parent UAV rotor. So in other words, as soon as you start deviating away from the body of the center of the parent UAV, your child UAV wants to get sucked into the nearest rotor. That's not good. These interferences may lead to instability of the child UAV, and this may even lead to collision between the child UAV and the parent UAV when the system does not respond properly. So that's in this podcast. And if you have any ideas on what you want us to cover here in terms of child UAVs and parent UAVs or marsupial UAVs or that, we'd love to cover them because they're really cool. And make sure to like, subscribe this, and check out our other podcasts, for example, podcast number 98, which covers the first half of this. And check out our courses on CFD and theory of aerodynamics. Links in the description. And I'll see you in the next podcast. Peace out, amigos.